Hello folks, Rashid here, and we are entering another phase of our RISC-V computer architecture. Okay, um, this part is related to the peripherals. So what we are going a little bit beyond just our CPU. And I think typically this part is not that very long, so I think I will cover it, finish it in maybe 6, 7 videos. Um, but this is my personal opinion based on my own learning that typically this part is not that well covered in books as well as in different courses or teaching, at least the one I have come across. Okay, so I will try to explain you some of the core concepts. We will look into examples. We will not look into every little detail because I think later on when we start looking into the next course, the next playlist, the next training after this one will be on microarchitecture, where we will take all the specs of RV32i that we studied in this section or in this playlist. We will implement them in System Verilog. So first of all, I will do a System Verilog tutorial, and after that we will start implementing it, and then we will test it. So when we will implement all the hardware, that's where every detail will come. Okay. All right, so I'm not going into details of what I've done, but what we did cover so far is just this CPU part. All right, we look into registers. Okay, I might put some register here, but these are those general purpose 32 registers. Each one of them was 32-bit. Then we look into an ALU part. Now we haven't looked into actual implementation, but we look into all these instructions, those 37 instructions, R type, I type, SB type, UJ type. Okay, and we look into the machine code, what kind of binary for each instruction will be stored in the memory, correct? And then we start looking into building our simulator and debugger so that would help us in terms of understanding, putting assembly code there and running it and seeing the state of the CPU registers and memory, right? So we did that, and right before that, we look into Python tutorial so that you have some basic understanding of the key commands in Python, so you can understand the code if you have to. But that simulator and debugger that I created was completely with AI. And I think that will help us a lot in maybe future, because right now we are already done, but maybe if I do a revision of RISC-V in 2 hours or something like that, then I will use that similar a lot, or the simulator a lot, but we will definitely use that later on when we go into System Verilog. But the point is, we have been just here, as well as interaction with memory, of course, but that's the other element, the SRAM that we interacted with. But that's it, right? Now, if you somehow are able to put, for example, this is SRAM, so when you turn off, the power off, the data will be lost. Okay, so every time you turn it on, you need to put data in it. You need to put your program in it. And then once you have a program in it, then PC starts there and execute all the instructions. And when it's done, eventually all the information will be the process information will be present in the memory, correct? All right, now how to take it out. Now how to use this system in a real-time way. In the real-time way, you will have some inputs coming from the output, from the external side, okay? From the outside, not the output, outside. Right? So the inputs will come, you will process something, and then you need to generate some outputs. I mean, that's what a system is going to do, right? Take certain inputs, not just in terms of this one, but some other interrupts will come, and you need to process that, and you need to generate output. For example, if this system is used in an industrial automation, for example, and it takes input like a temperature sensor, And based on the temperature sensor, output or the input that is coming to the system, it will sense it, and maybe you need to turn on a fan if temperature goes beyond that level, or turn on AC, or do something, or turn on a motor or something like that, right? So that's where our RV32I will have a majority of application. So in that case, you need to connect your temperature sensor or any kind of sensor input, and you need to control some output. Of course, you need to process some data here, and then generate outputs. But how to do that? Right now, all the instructions are there for processing, but that interface is missing. Okay, and that interface is what we are going to do. We're going to look next in this part of the RISC-V computer architecture specs. So here is the bigger picture. So this is the RV32I that we studied so far. Now there are some parts, like what I call here CSR regs, which are very special registers. Okay, we haven't studied them, and those are not that many, just I don't know how many, 4, 5, something like that. So, and those are 32 bits. So we will study them, but that is some additional thing that we will cover. And this one I call like a ALU, just here is just where addition or arithmetic operation, logical operations are done in here. And then we also need some muxes here and there to control it, right? To process, okay, where we want to direct in output to register, to memory, blah, blah, all of that. So that's these two blocks correspond that. So CSR regs, control status registers, here is something we're going to study. Okay, and these are registers. We have done that. All right. We always refer to an SRAM, an external register. Remember how much is the address bus? Address bus was 32-bit, right? We were saying 32-bit. So that means we can access the data of 4 gig. But in our system, we need a flash. Okay, so when the power is off on flash, its data still stays there. So that's cool thing. On our PCB, we can put inside a chip. I mean, this entire thing can be inside a chip, or we can have this thing inside chip, or we can have this. I mean, SRAM is good to be on chip, right? Because it's going to be fast. So, but I've seen it because with everything comes as controller, right? It's logic that needs to interact with the rest of the world. So, okay, let's say we have flash outside a chip. This part is within a chip, but still on the PCB, you need to put your instruction into the flash once. And every time power is on, the flash data will be read into initially by the CPU. So you have startup code and all that is there. Okay, and we will study when the reset comes, we started what kind of operation happens in order to start, initialize everything and have the processor ready to execute. But our basic code will come from here. It can be copied later on here and processed from here, but initially it will be here. All right, so flash need to be connected. SRAM we already studied. Okay, we need to have stack there. We need to have global data. We will study about that. What comes to SRAM, but we need to have some data there. We need to process. The outside world, okay, you on your chip, I should have put a chip interface, but on the chip interface, you have a lot of general purpose IOs that you can use them for different purpose. So they are coming from here, and there's GPIO controller which is connected to all those. So that's where input is coming, and that's where the output will go. So they need to be connected. Okay, how are they going to communicate with CPU? You can have some other interface devices like this UART. You can have I2C, those low frequency protocols, right? In embedded application, that's where our RV32I is going to be used. So we need to have those ones. How are those going to talk to CPU? Right? Think about that. Then this is a very important component we will study during maybe in the next video and after that, interrupt controller. So all these devices are connected here, and they control kind of access to you, communicate through this. They initiate the access through interrupt controller. Okay, so this is the minimum system. And also in our RV32i, we're not going to use any operating system. Okay, it's gonna start right from here, and our program will be the king. It can do anything. It can access any register, any memory. Okay, so it's kind of has a full privilege. So we don't have like operating system there which has more privilege than user application has less privilege. This is simple system for embedded application, low power, and I like simplicity. So we will start with this simple system. Okay, so you need to have all these things. So how are these things going to work with CPU? So the way all these things communicate this, you have this system bus. I think there can be different protocols. There can be an open source AHB, I think of Wishbone, and those different names that you can search. So their thing is they have an address bus, data bus, control bus, and all these devices are connected to them. CPU acts as master, these acts are like all slave in our system. But they all communicate through this. If this want to access here, something here, it sends an address. Through here, it sends an address. And each device knows when it's being, when the address is coming from it or not. We'll look into some examples. All right, that makes sense, the higher level picture. Now, in order for CPU to kind of access each of them, and I just gave you a hint that each one has an address. Remember, the address bus is 32-bit. So these are different houses. Okay, each one, these are, let's say, not houses, but these are neighborhoods, right, or street. And inside each this street or neighborhood, there are different houses. There are different locations, memory, or different register within interrupt, or different register within these things. That each one can have a different address. Those are different houses. So those addresses are part of those 32-bit. So here is something new you're learning. Those 32 bits that we thought all of them are for SRAM are actually not for SRAM. It's still an address. So CPU accesses as if it has a one continuous line of addresses. But actually we know that we have assigned some addresses for this, some addresses for this, some for this, some for lot for this, and some for this. So this is called like a address mapping, or the memory space, certain parts are mapped to different things. So this we will go into the next stage, which is here. And by the way, these are the topics that we're going to study. So right now we'll do memory space mapping, which I'm thinking maybe I should do in the next video. So actually, let's do this. In the next video, we will do memory space and mapping. So we'll look into that. That is an important concept for you to understand. Then we will look into when an interrupt comes. Let's say this GPIO is connected to the outside world and temperature sensor comes in. What is the whole process, how CPU, it communicates with CPU and they exchange data. And when CPU wants to, let's say, for example, it sends a signal to a fan or AC or motor or something, it sends one signal. How does it send that signal? So, and then exception is another important thing. Exceptions are when some illegal instruction comes in a program. Right, and a binary comes in and it doesn't have any equivalent instruction. What happens then? Or the address for instruction is not like byte aligned, or maybe some illegal instruction comes. Did I say that? Or maybe some address comes which doesn't exist. So all those kind of error type of things, when they come in a code, we need to have some of those are called exception. We need to handle those cases too. The interrupts and exception together call those traps. We will also look into maybe assembler. Yeah, maybe I think it's better to have it at the end. There's some of the directives, some of the assembler related, they don't have effect on the binary code, but some of the special commands within assembly language that you can put there, and you can say, okay, this is which part of the address space. So we will look into some of the examples there. But hopefully once we've gone through, you will be well prepared for that. So we'll do a 5, 6 or 6, 7 videos on it, and then you will get a full idea of that. All right, interesting, isn't it? So, all right, that's it for now, and I will see you in next video.